All right, students, I got another great question here. And as you're working along, and it's about 21, so another one here on circuits. But it's number 20. And let's just read it together and kind of go through it here. It says a car battery with a 12-volt EMF and an internal resistance of 0.05 ohms is being charged with a current of 60 amps. So let me pause right there and kind of make a little picture. Maybe I'll put a little circle and saying, all right, here is the car battery. And the car battery is being, as it says, charged because 60 amps are being put through the battery in a reverse fashion. In fact, maybe it might be a good moment to kind of stop and kind of understand the idea of a rechargeable battery. And so we like to use this symbol that kind of shows the chemical potential. To be quite honest, the car battery would have multiple cells, so 6 of them actually. I don't think I have enough room to draw all 6, and that's normally not what you draw anyways. When you have a multiple cell battery, you tend to draw just 3 of them to indicate it's multiple, not meaning there's 3. So I'll do 3, but there's a chemical reaction, and let's see, so this is a car battery. So we've got a chemical reaction between lead oxide, and the sulfuric acid. And let me not get into a long discussion about the chemicals involved, but you're probably also familiar with probably the more common one is the lithium battery and the chemicals that go on in there, or the nickel metal hydride ones. Anyways, there's a lot of very interesting set of chemicals that they want to react and shoot electrons out. So in this case, I guess this will be the negative part of the battery, and this will be the positive part of the battery. As the chemical reaction takes place, it shoots out a negative, shoots out a negative, shoots out a negative. And you get about 2 volts, a little more than that, 2.1 volt, but I'll just call it 2 volts here, since if we had 6 of them stacked up, we would be having a total of 12 volts. And that's what they say. So that's what they mean here by the EMF. There is a certain amount of voltage that is created by the chemicals that are inside. Now, of course, to get the electricity in or out, you have to build this. And in this case, we would have a water solution of sulfuric acid. And then we would have our 2 plates. One would be a lead plate and one would be a lead oxide plate. And in the process of those coming out, they've got to move through the metal pieces and through the liquid. There's going to be some resistance. And so this is the R. Try to make it as small as possible. We would prefer, in an ideal world, not to have any internal resistance. But again, you got to have some, just because the electrons got to flow through the construction of the battery. So when you run it in what I'll call the reverse direction, so notice this is the plus here, because a normal way that you might think of a battery, which makes sense when you're using it, is if I was using a battery, let's just say I'm using the battery in my phone. I got my lithium and my other metals that are in there, but I'll just call it a lithium ion. And it produces about 3 volts in the chemical reaction, and it comes racing out, and then there's some resistance. Not only is it in the wires of the phone, but then I want some resistance probably added there so I don't drain my battery too quick. And maybe that part of this process is a little LED light, so I'll just pretend this is one of the mini LED lights that are in my phone. And you can imagine a phone's doing much more complicated than this. But my point is the chemicals are being used up, and the battery is being drained, and the current flows in this direction. When it comes to recharging it then, what I'll do is plug it in, and usually to a USB port that will have 5 volts. And that 5 volts will send in so much current that it will continue on and run my phone, so my phone can operate while I'm plugged into the USB. But in addition to that, the current will split at this node and go through the battery in a backwards direction, forcing it in reverse and undoing those chemicals. And so now I am separating then the electron from the ion, whereas before I was bringing the electron together with the ion, and that's why it's called the lithium-ion battery. Here, I'm trying to remember the chemical here. I guess we're making lead react with the sulfate. So we're making lead sulfate when the battery is being used, and then when we're charging the battery, which is what this process is saying. And so while the car is running and my alternator is producing the current goes through the battery in a reverse direction, undoing that lead sulfate and changing it back into just lead and sulfuric acid or lead oxide on the negative plate. Okay, so again, probably said too much about the chemicals. I just want you to then understand that some chemicals are reversible and some are not. So the ones that are not, like the alkalis, they make great chemical reactions, but they're not rechargeable. That is, if you run electricity in reverse, they don't undo the chemicals. The chemicals are stuck together so hard that they don't undo themselves. So we can't recharge our alkali batteries. We have some batteries that are rechargeable, some chemicals that undo themselves, and others that don't. Other ones you have to put it in the recycle center, and you have to separate the chemicals through a chemical process before you can make a new battery. You can't just run the electricity in reverse. So if you didn't already know that, that's kind of an important part here in this question here. And to understand what's going on is that I'm sending 60 amps reverse through this battery. So if this is already 12 volts, then we're going to have a little voltage drop here, and so my power supply needs to be something greater than 12 volts. And if you have a car like I do, it's got a little voltage gauge on there, and usually I'm running about 14. 14.1 seems to be a common number for my car. And so I'll look down on the dashboard and say, hey, what's the voltage right now being generated to recharge my battery now that I just started my battery? And so, yes, definitely greater than 12 volts. All right, so let's get to the heart of the question here finally. It says, note that in this process, the battery is being charged. Okay, A, what is the potential difference across the terminals? So in other words, across here. And as I said, it would be 14 plus whatever this drop is. Or maybe to put it another way, if we do our loop rule here, and we say, okay, this is some other charging battery. So I'll just kind of make a V for my battery there. And if I add up around the loop, starting down here, I would go from negative to positive. So this is really my alternator of my car. Let me call that a V. Then I can go across here, and then since the current would be flowing this way, the voltage change here would be Ohm's law, current times resistance. So current is 60, resistance is 0.05, and I'm going with the current, so that's a decrease. Then I go through the internal EMF, which they tell me it's 12 volts. It actually would be, as I said earlier, 2 volts 6 times, but again, it would be a minus 12, and then I would return back where I started. So there's kind of that Kirchhoff's loop rule, the principle of conservation of energy. Or put another way, the voltage would be, and I'll move the 12 to the other side, so that's a plus. And then I'll move this to the other side and even multiply it out. Let's see, 5 times 6 is a 30 with another 0 and then 2 decimal places. So that's going to be 3 volts. And so 12 plus 3 is 15. And so the first thing to say here is for this to be happening, I'd have to have 15 volts on my charging system, because as it runs through this, I lose 3 and then I lose 12 more. And so this is just making heat. And I think that's kind of the next part of this problem. It says, at what rate is thermal energy being dissipated in the battery? So my goal is not to make heat for this battery. My goal is to undo this chemical reaction and to feed energy into, as I said, undoing the lead sulfate and going back into sulfuric acid and lead. But in the process of getting there, I've got wires and connections and metal plates, and so there is some resistance, and so this is the part that is generating the heat. And so this is what I want. This is what I wish I didn't have, but I'm stuck with it. That's why my charging system has to be greater than 12. And the greater it is than 12, the more current that would flow, and the faster I'll charge it, but also then the more heat I will make. So really, when they say in part B, what is the rate of thermal energy being dissipated in the battery, they're asking for this number. And so let's see, I guess this was A, and so then B would be the energy in that internal resistor, which we could write as I squared R. I guess we could also write it the other forms, but this one seems to make the sense because we know the current is 60, so I'll go 60 squared, and the resistance is 0.05. Which I guess we know that times one of the 60s we just did is 3, so 3 times 60 should be 180. Maybe I'll just grab my calculator and double check. And yeah, it's 180. So it's 180 watts. So the battery's going to be warming up, and that's, of course, what they're trying to say here in B. And then C, at what rate is electrical energy being converted into chemical energy? And so that's why I had to go on that long-winded discussion at the beginning and say, okay, what's really going on here? And this is the part they're talking about. They're talking about charging that up. And so let's look at the other formula. This was one formula for power, but another one would be VI. And of course, another one would be V squared over R. And of course, you can see for B, it made more sense to do this one. But for C, it makes more sense to do this because we know that the voltage that we are building up or creating the EMF is 12 volts, and we know we got conservation of charge. That is, the current that comes through here has to go 60 through the resistance, but also 60 through each of the 6 cells. So we know the current is 60. And so what is it? 12 times 6 is what? 72, and then a 0. So we've got 720 watts for the energy that is currently being stored. That's the part C. Now, here's what's kind of an added fun part of this. It says, now, what were your answers to A and B when the battery is used to supply 60 amps to a starter motor? And so here's the important difference. And so let me keep this in mind, because now if I take my battery, okay, and I have this EMF inside, and then this internal resistance R, 0.05 ohms. And so here's kind of the edge of the battery. Here's what the physical thing you would see if you lifted the hood on your car. You would see this lead acid battery. And there'd be a terminal, which you'd label as positive, and over here you'd have another terminal, which you'd label as negative. And you'd say, okay, I'm going to use this then to run a starter motor. So I'll just kind of represent the the motor here with a load resistor R, which is why I probably should put little r here. That's why we like the little r. Not only does it represent a small amount of resistance, but it separates it from what we're trying to run, and this is our load. So this is our starter motor. But what's important here is to recognize now the current is coming from our chemical reaction. And so here's where our lead is now turning into lead sulfate and our sulfuric acid is turning into water. And so we would then be running the 60 amps in the other direction. Okay. And so if we come back here to A, what is the potential difference across the terminals? Okay, now again, we're calling this V. But the current's going in the other direction. So D would look like A in the sense that I might start here on my loop and go, okay, here's the V from the terminals. And then I have this voltage change due to the internal resistance and the current. So this is our IR. I guess I is 60 and R is 0.05. But if you'll notice now, I'm going against the current. And so it would be an increase as opposed to in A, we went with the current. So with the current, I put a minus sign. Now I'm going to put a plus sign. Now the other one doesn't change because when I go from here to here, it's again an EMF, a change of 12, and I go from the big bar to the little bar, so it's still a minus. And so that's exactly what we did in A. So that doesn't change. And so the only thing that changed is the sign here, because remember the sign for the resistor depends on which way you are going around the loop compared to the current. The plus and minus for the EMF or power supply is just, you know, the big bar to the little bar. And so sometimes you put a plus and sometimes you'll put a minus. And in my case, let's see, what did I do? I went from big bar to little bar. So I put a minus. And in this case, I guess I'm doing the same thing, big bar to little bar. So I put a minus. Okay. I thought for a minute there, I thought it was looking different. Anyways, that equals to 0. And of course, I think this still comes out to be our 3. But of course, now we've got a V equals, and when I move the 12 to the other side, it becomes plus, but then it's minus 3. And so that's 9 volts. So in other words, we're only supplying 9 volts to the starter motor. And hopefully that makes sense, because the chemical reaction is producing 12, and we lose a little bit, 3 along the way, so the energy left is 9. So chemical gives us 12, we lose 3 trying to get it out, and so we only have 9 that is going to the starter motor. Whereas when we were charging this battery, we needed to supply 3 more greater than the 12, because we had to supply an energy of 12, but we would lose 3 along the way, which is why we had to supply 15. So charging it, we need to supply it 15. Discharging it, we only get 9 after we lose the 3 from the 12. That's the kind of the important difference here. Okay, and then finally on to D. Okay. Well, I guess it's not part E, but it still says part B. And so part B, at what rate is thermal energy being dissipated in the battery? And in this case, it would be this I squared R. Oops, and I should put a little r. I squared little r. So it's still the 60 squared, and it's still the 0.05. So it still comes out to be the 180 watts. In other words, we lose 3 trying to get out, just like we lose 3 trying to get in. It's just, that's why we have to have 15. We have to have 3 greater than the EMF getting in, whereas over here, we start with 12 and we lose 3, that's when we only have 9 coming out. And so whether we are charging our battery or discharging it, there's going to be some thermal energy. And again, you probably notice this well with your cell phone. When you plug in your cell phone and start charging it up, it will feel warm. And that's this part. You're charging it up. But also, if you're using your phone, and so you're not charging it, but you're using your phone, and you're doing a lot of, especially if you're doing a lot of processing, you can feel it get warm in your hand, or sometimes I'll leave the screen on accidentally and put it in my pocket, and I can feel it warm in my pocket, and I go, oh, I left my screen on. That's not good. My battery will go dead. So either way, it's dissipating the same amount of energy. Okay, hope that was helpful to someone. Take care.